Here I'm going to go through a Leaving Cert past paper question on acids and bases, or pH calculations. It's from 2020, it's question 7. It starts off in the usual manner, looking for a definition of a Bronsted-Lowry or an Arrhenius acid or base. According to Bronsted-Lowry, what is an acid? Okay, so I'm going to describe this in a little bit of detail here. So an acid is a molecule which is able to give away a hydrogen ion or a proton. So here we've got a hydrogen attached to a molecule, any other part of the molecule. It'll form an anion, that's why it's called an A. So that's HA. And what I'm going to do is I'm going to react that with a base. And for now, I'm just going to give water as an example. Now what happens is the lone pair on the oxygen simply takes that hydrogen and the electrons jump onto A. And if you want to know more about the curly arrows and a reaction mechanism, have a look at the organic chemistry part of the site. But you end up forming H3O plus, the hydronium ion, and you end up forming your A minus. So according to Bronsted-Lowry, an acid is a molecule which is able to donate a hydrogen ion. So according to Bronsted-Lowry, an acid is any molecule that is able to donate a hydrogen ion or a proton. So here it's a proton donor. So a proton being H plus ion. Now we're going to look at two systems where this happens, okay? So I'm going to look at HCl, and I'm going to use the colors HCl. We form H3O plus Cl minus. Okay, so this is a strong acid and it is a good proton donor because the water readily takes that hydrogen. In fact, it automatically does. The minute HCl becomes in contact with water, that oxygen takes the hydrogen and the electrons jump onto the Cl to be Cl minus. I'm just going to change the color of this here. Okay, so any molecule which readily gives away its hydrogen to form H3O plus, let's just remind ourselves this is the hydronium ion. That's actually the source of all acids, the hydronium ion. Okay, so if there's any hydronium ion in solution, basically that means it's an acid. But it has to come from somewhere, so it comes from an original molecule. If the molecule easily gives away its hydrogen ion, then it's an acid. But sometimes though, not all acids are strong acids. So we do have an example where, let's say you've got CH3 COOH, and this is just ethanoic acid. Okay, if that molecule is introduced to water, okay, you form H3O plus, and I'll talk about those arrows in a minute. H3O plus this thing here, okay, which is the ethanoate ion. And it just so happens that the reason I've drawn these equilibrium arrows, and the equilibrium is far to the left here, water isn't as capable of taking the hydrogen of ethanoic acid as it is of taking the hydrogen of HCl. One of the reasons being the ethanoate ion isn't as stable in solution as the chloride ion. In fact, it just prefers to be in the state where it's bonded with the hydrogen, so ethanoic acid. So here you've got a weak acid, okay, and it's just a relatively poor, or it just doesn't break up as much. Weak acid, so it's poor. I can actually use these equations to talk about the different definition of an acid, and that is our Arrhenius acid. Now an Arrhenius acid is an acid that dissociates in water to produce hydrogen ions. So here I'm showing the water taking the hydrogen from the molecule and becoming H3O plus. The other way of looking at it is actually the molecule just breaks apart or dissociates into its ions, and the easier that molecule finds it to break up or dissociate into its ions, the stronger the acid. So according to Arrhenius, a strong acid will fully dissociate in water, whereas a weak acid partially dissociates in water. Okay, but essentially the same process is happening. You've got a molecule which is essentially losing a hydrogen and just the hydrogen ion to form H plus, which effectively will form H3O plus because there'll be water there in solution. And this is the source of all acids here. hydronium ion. All acids are hydronium ions. Okay, doesn't matter what you started with, you will form H3O+. That is a substance that's really corrosive. Okay, so I've gone on a bit about that there, but just to talk about acids and bases. I'll now go on to the rest of the question. Okay, so the next part, B. What is the conjugate acid and the conjugate base of HSO4-? Okay, so we're going to talk about conjugate acid-base pairs here. Now, essentially what happens in solution, if I have H2SO4 and I've dissolved that in water, what happens is the water, just like in the previous case, will abstract a hydrogen ion from the molecule. So you're left with HSO4- plus H3O+. Now, what can happen a second time with this acid is water can abstract another proton and you form SO4-, the sulfate ion, plus H3O+. Now, I'm just going to change the arrows here to equilibrium ones for now. For more on that, see the equilibrium section on the website. So, I've set up the equilibrium system here of H2SO4 dissolving in water. The water will abstract a hydrogen, so you get a chemical reaction there to form HSO4- and H3O+. So you've got your acid and you've got your base forming an acid here, and you're also forming a base. Because if this is reversible, i.e. now going in this direction, to reform the reactants, the HSO4- would have to take the hydrogen back off the H3O+. So that's a base. So what we do is we refer to them as the conjugate acid and the conjugate base. As I said though, with sulfuric acid, it can dissociate again. So in this instance, when it's reacting with H2O, the H2O is reacting as a base. We're now looking at this reaction here. The H2O is reacting as a base, but actually in this instance, this is reacting as an acid to form your base and acid. Again, they'd be conjugate base and conjugate acid. So actually the HSO4- can either act as a base going in that direction, or else it can act as an acid going in that direction. So when it asks us what's the conjugate acid of HSO4-, the conjugate acid of HSO4- is H2SO4. The conjugate base of HSO4- is here, SO4 2-. Okay, so for B, the conjugate acid is going to be H2SO4, and the conjugate base is actually going to be SO4 2-. Because that can act in two ways. It can either go in the green direction to form H2SO4, or in the yellow direction to form SO4 2-, theoretically. Just going to tidy this up a bit. Okay, so the next part. When carbon dioxide is pumped into mineral water, it becomes sparkling water. The information shown in the table was given on the label of a sparkling water bottle. Describe how you test for the sample in the mineral for the presence of the sulfate ion. Okay, so they threw in this question last year for testing for ions. It's important to know, again, it's a bit of recall material from the experiment section. To test for a sulfate, you first add, you can add nitric acid, but to start with you'll add, the actual test for the sulfate is barium chloride, BaCl2, and what should happen is you get a white precipitate, okay? PPT is just precipitate form there, okay? So that's just an insoluble solid. What happens is the barium and the ion and the sulfate ion come together to form an ionic lattice which is insoluble in water. So while your sulfate would originally be soluble in water and you wouldn't notice it by looking at it, the minute you add a soluble barium chloride to it, okay, so you have two coloured solutions, you form this white precipitate because the barium ions and the sulfate ions come together to form the lattice. So I'm just going to tidy this up a little bit. So for D, we've got a pH of sparkling water 5.6 and the pH of the water source is 7.2. Calculate the hydronium ion concentration of the sparkling water. Okay, so for these type of calculations, there's a few things to note. First of all, to work out the pH of any solution, it's going to be minus the log to the base 10 of the hydrogen ion concentration, which is the hydronium ion concentration really. So to work backwards there, using our maths, we can just say that the hydrogen ion concentration, or the hydronium ion concentration, same thing, is equal to 10 to the minus pH. So if you're asked the hydronium ion concentration in this, it's going to be 10 to the minus 5.6, which when you put it into the calculator works out as 2.511886. But we're given two significant figures in the question, so we may just leave it to that. 2.5 by 10 to the minus 6. As its concentration, it'll be moles per litre or moles per decimeter cubed. You then ask the concentration of the hydroxide ion of the source water. Okay, so for this we're going to be using Kw, which is the ionic product of water. For more on that, see the video on the website. Kw is equal to the hydrogen ion concentration, or H plus concentration, times the OH ion concentration, which is actually equal to 1.0 by 10 to the minus 14. So in the question they're asking us for this. So to work that out, well really what I need to do here is I need to work out what H3O plus is and plug it into that equation. Well, how do I get H3O plus? Well, I'm going to use the pH because it's telling me the pH is 7.2. So pH equals 7.2, hence H3O plus equals 10 to the minus 7.2, which is 6.30957, 6.31 by 10 to the minus 8. So it's a really low hydrogen ion concentration. We're not surprised as it's slightly alkaline. So to work out the OH minus then, OH minus, we're going to use our first equation, is equal to 1 by 10 to the minus 14 divided by 6.31 by 10 to the minus 8. Okay, or else you can just use that figure in the calculator as your answer. So the figure for OH minus concentration is 1.5848, so it's 1.58 by 10 to the minus 7 moles per litre. If you don't want to use this equation here, you can actually just from the pH work out the POH by subtracting it from 14, and from that then you're able to just put 10 to the minus that and you'll get this answer here down the bottom. I'm just going to tidy that up a bit. So we're on to the last question. An acid-base indicator, which is a weak acid, may be represented by HA, like I did at the start, HA. The indicator is red in its undissociated form and yellow in the form A-. Calculate the pH of an aqueous 1.5 by 10 to the minus 3 molar solution of indicator, which has an acid dissociation constant of 4.0 by 10 to the minus 4. So I'm just going to go through that in a bit of detail to start with. We know that for any acid system, HA, when it breaks up, it forms H plus plus A minus. So because it's an equilibrium, Kc is just going to be H plus, or H3O plus, times A minus. Remember, I could do it with H3O plus all over the concentration of HA. Now, so this is an equilibrium. So as it's an acid dissociation, we refer to Kc as Ka. So therefore, Ka, and if I multiply both sides by Ha, I've got Ka times the concentration of acid is equal to H plus times A minus. But if you look at here, for one of these you get one of these and one of these. So for a monodissociation here, you've always got the same concentration of H plus as A minus. So H plus equals A minus. Therefore, Ka times Ha is equal to H plus squared. So H plus is equal to the square root of Ka times Ha. So that's how we work out the, especially for a weak acid, the H plus ion concentration. And we can work out pH, because that's equal to minus the log to the base 10 of H plus. Now I know here I've used H plus instead of H3O plus that I used previously, but I essentially mean the same thing. But that's just how we derive the formula for working out the hydrogen ion concentration of a weak acid. Just move that around there. So we're asked to calculate the pH of a certain concentration of indicator with its acid dissociation constant. So to work out pH, we need minus the log to the base 10 of hydrogen ions. So we need to work out the hydrogen ion concentration first. So part E, H plus is equal to square root of 1.5 by 10 to the minus 3 times 4.0 by 10 to the minus 4. And you just put that into your calculator. So we're left with H plus equals 7.745966 by 10 to the minus 4, and you can just keep the answer that's stored in your calculator there for the next part. So we're looking for pH then is equal to minus the log to the base 10, so just keep the answer that's stored, or else you can do it all in one step obviously. So you're at minus the log of your answer, and that becomes 3.11. So you don't need to go through all the theory for that. To answer that question, you just need to remember this formula and the lower one and plug in the numbers. So I'm just going to tidy that up. Now for F, write an equilibrium equation for the dissociation of the indicator in water. So if your indicator is HA and you're dissociating in a water, you're forming H3O plus as usual plus A minus. So it's the same equation I wrote at the very start of the video. What is observed when a few drops of the indicator are added to a solution of the strong base? Explain your answer. Okay, so we're told that it's red in undissociated form and it is yellow in this form. Now, what's observed when a few drops of the indicator are added to a solution of a strong base? Well, a strong base, so the base will automatically remove H3O plus. So if we think of our acid equilibrium, the base will remove this, so the concentration of this decreases, the H3O plus, so the equilibrium will re-establish to make more of that. Okay, so if the equilibrium re-establishes to make more of A minus, then the color will go yellow. So solution turns yellow, becomes more yellow, because H3O plus ions are removed, equilibrium shifts to make more. So position of equilibrium, and so we see a yellow color, because automatically if more of this is being formed, the H3O plus, we form more of A minus. Okay, and that's that question done. So a lot done there, but have a go at practicing some of the other questions on acid and bases or pH calculations, okay?